All right, let's get this party started. So, number one, Kyle defines a circle as the set of all points equidistant from a given point. What is wrong with Kyle's definition? It's not precise enough. Well, if we have, how he has this worded is if we have a point and he's talking about the set of all points equidistant. So here's my fixed point and I'm going around. Okay, that kind of makes sense that that's a circle, right? But what if I go this way? Or this way? He's not talking about a circle, he's talking about a sphere. So what he has to specify is that it is on the same plane. Or on a plane, whatever. Alright, you have to specify that. On a plane, on the same plane. You get it. We've done that before. Alright, for this one here. Now I don't want you guys to get too hung up on the actual proof because you guys see this and get confused every time. I know this is kind of hard to read up here, that's why you have it right in front of you. It starts out talking about two parallel lines, so we know we're going to use that. Just look at the empty boxes. Here it says F and H, that's that baby there is congruent to RWV, that's that baby there. Well, what do you know about those two angles? They're what? Corresponding. That's your answer right there. So you're going to pick and you're going to go, this is reason 3, so you're going to go from this column. And it's the third one down. If two parallel lines are cut by a transversal, the corresponding angles are congruent. You take that, you pick it up, you drop it into the box. Something I want to point out about that. It could also say the corresponding angles theorem, right? Okay. If you guys accidentally, let's just say you did this one here about alternate exterior angles and you drop that in the box. I don't know if this is going to happen, but I do know when we took the practice test in the lab, and if you did that and made a mistake, there was no way to take it and drop it back out to where this box was empty again. All right, so just be mindful of that and be careful. If you make a mistake, it's okay if you do that, but you have to just replace it with the right one. I didn't like that. You know? Oh well. All right, the next one says that NPR, that's that dude, is congruent to RVW, that's that dude. All right, what is their angle relationship? Alternate interior angles, good. So then you just take the one that's talking about alternate interior angles, which is here, and you drop it into the box. That's it. All right, this one's pretty cool. This is talking about construction, and it says, this is only part of a construction. So you hit play, this is where it ends up. So he still didn't even finish it. It says, what will be the result of Rubin's construction? Well, a lot of students thought the answer was B. That's not it. I'll talk about that in a minute. The answer is D. What he is doing is he is constructing the angle bisector of angle B. Real quick. Oh, yeah? All right, real quick. By the way, check out the constructions link that I sent on Skyward. Did you guys look at that? Okay, you need to know all those constructions. It has the directions too, so you're good to go. So real quick, if I have an angle B, all that I do if I want to construct an angle bisector is I take my compass, I put it on the vertex, I go shh, then I pick it up and I go here and I make a little arc. Look, that's where he stopped. What he would need to do next was, without adjusting his compass, go here and go boom there. And then you take your pencil and straight edge and just, whoosh. That's good. Look at that. Yeah, that might be the best one. That was freehand. That's how you construct an angle bisector. Now what he's talking about here with B, just real quick, he's talking about bisecting the segment. If we do that, so you have a segment, when you're talking about bisecting a segment, it is the perpendicular bisector. You also make the midpoint of the segment. So all of those things, you do the same process. You take your compass, you pick a point, and you go here without adjusting the width. You go here. Pick it up. Do not adjust. Here. By the way, I stretched it more than halfway. I probably should have said that. You move it to this point, and then you go shh. Notice how I didn't pick up my pencil that time? Because it doesn't matter. You'll see it both ways. Then from there, you take your ruler and straight edge and connect. Oh, that wasn't bad either. But that constructs the perpendicular bisector. Yes, honey?
I thought that when you construct the segment that goes to only one line and stuff, like how they change before you drop it in the middle.
Do you mean this right here?
Yeah.
He does. He still, that's a really good question. He did this part, and then he did this part. He still needs to go here and do this right here.
Yes.
Okay, but look what it says, part.
Oh.
So yeah, that's good to point that out. This is a little tricky. When he finishes, that's what he's gonna do, and then he's gonna go like this. Okay? Always count on Zach to ask the good questions. All right, this is the good one. Kendra. Hey, I'm good. Geometry all day. I want an extra day with my honors kids though. My on-level kids are testing tomorrow, and then my honors are testing Thursday, Friday. So Mr. Vanyo, I'm gonna yes, he's Tuesday and Wednesday. He's gonna fill in for me. Yeah, but his kids are done, so pretty much, because he's algebra 2. Tomorrow, I'm going to go in the morning and sub for him because, not tomorrow, yeah, tomorrow. Sorry about that, because my on-level kids are tomorrow. And so, yeah, we have it all worked out. No, thank you for approving it. Yes, ma'am. Thank you so much. You're the best. Bye. All right, good. Sorry, guys. All right, back to business. This is a diagonal of a square. It is asking us for the possible coordinates for point F. So this is a diagonal. The other diagonal is going to go this way. You know that the diagonals are congruent and the diagonals are perpendicular. Nice, good job. Perpendicular. So that point is going to be here or here roughly. We're going to find it exactly though. All right? So we have to look at, I'm going to start with midpoint actually. If I go from here to here, we can just count this. We go up 1, 2, 3, 4, to the right 1, 2, 3, 4, 5, 6, 7, 8. Yeah? So the midpoint's going to be half that, up 2 to the right 4, right there. Real quick, shortcut for midpoint, take your points. This dude is at -3, 0. This baby is at 5, 4. That's an ugly 4. Oh my gosh. Are we good here? Okay, you stack, you add, so this is -2, 4, and divide by 2. Stack, add, divide by 2. That's our midpoint shortcut. Why did I get?
Yeah, it's probably.
Y'all got me. Sorry. What? What? Alright. So it's 1, 2. Alright, moving on. Jeez, I can't believe I just did that. Alright, now from here, we're going to think about slope. We already know that, actually, I'll do it this way. From here to here, we go up 2 to the right, 1, 2, 3, 4, yeah? Okay, that's our slope. 2 over 4, rise over run. We need to examine the perpendicular slope. If this is positive, this is going to be negative, and we flip it. So it's going to be a -4 over 2. This is what we're going to look at. So from the midpoint, we are now going to go, if I go down 4. 1, 2, 3, 4. Do I go right or left 2? If I do that, that is a positive slope. So don't make that mistake. If you go down 4, you have to go to the right 2. Okay? Good. So there's 1, and then now I'm going to go this way. So if I go up 4, 1, 2, 3, 4, I have to go to the left 2. Right here? Yeah. Are we good? So this will go here, this will go here. I'm going to draw a little square. You don't have to, but whatever. So that's what we have going on. Yeah, I'm on it today. All right, so point F could be at -1, 6, or it could be at 3, -2. Yeah? So when you hit this drop down, whatever it says, one of those, choose it. And then of course it says because the diagonals of a square are congruent and perpendicular. Awesome. All right, this is a nice one. This equation is shown. Line A and B are perpendicular, and this point, -2, 1, lies on line B. Write an equation for line B. So, we already know y equals mx plus b, where b is the y-intercept, and m is the what?
Slope.
Good. This is saying that they are perpendicular. If they said they were parallel, then the slopes would be the same. Perpendicular means opposite reciprocal. So right now, our slope is -2/3. Our perpendicular slope is going to be what? 3/2? All right, so that's what we're going to use. Now, because it is telling us that this point lies on the line, our y-intercept is going to matter. So what I'm going to do is I'm going to say, okay, I'm going to start making this equation. Y is equal to 3/2x plus b. This is going to matter. So what I'm going to do is I'm going to plug in -2 and 1 for x and y into this equation. Yeah, good. When we do that, we'll be able to solve for b. Where I see y, I put 1. Now right here, be careful. That's still a -1 in there. Don't lose that. So this is going to be 1 is equal to -3 plus b. B is equal to 4. Yeah? So now you just go back to your y equals mx plus b form, and we're going to say, okay, y is equal to, where I see m, I'm going to put that. 3/2x, and then I'm going to put plus 4. That's it. All right? If this was a -4, we would write -4. Questions? Okay. All right, this problem here. Oh yeah, I had a computer meltdown last class, that's right. This is a partition problem. See, now we have all this downtime right now. I actually deleted this whole file on an accident last class. It was bad. What is happening? because points A, B, and C are collinear, which means on the same line. Collinear. Coplanars on the same plane. Good. AB to AC is 2 to 5. Point A is located at -3, 6. Point B is point B we don't know. Point B is at NQ. And point C is located at -3, -4. So, there's our segment. So, you guys, B is somewhere in between these. And this is where we need to be careful. It says that the ratio of AB to AC is 2 to 5. Remember before the problem we did last class where it was find the point that divides the segment into a ratio of 2 to 3? And so it was asking for the point that was 2/5 of the way. The way this is worded is a little different. This is saying we're already in that ratio, 2 to 5. So B is that point that is 2/5 of the way. Any questions on that? Okay. You good? Okay, cool. All right, so same thing we always do. Take your points, stack them up. A is at -3, 6. C is at -4, 10. Nope, -3, 10. Jumping the gun, sorry. B is somewhere in between. All right, guys, how do we get from here to here? 0. We did nothing. We literally added 0. So that means this here is going to be where?
On 0.
Not on 0, at -3. Look at the segment. It stays, right? It's an easy one. All right, so now you look here. How do we get from 6 to... What happened, you guys? What the heck?
It's supposed to be negative.
What in the heck? You'll see why I wrote that, because my brain's working faster than, I'm sorry. We're fixed. How do we get from here to here?
-10.
Man, you know what I'm going to do? I'm going to... Hold on a second. When did Miss... Never mind. We'll just leave it. Okay, yeah, we subtracted 10, right? Guys, that's 100% of the way. We don't want 100%. We want to go how much? 2/5 of that. So just multiply. Yeah? What do we get?
4.
Positive or negative? Negative, so don't forget that. So it's going to be, instead of subtracting 10, we're going to subtract 4. What's 6 minus 4?
2.
2. Hooray. So B is at -3, 2. And that makes sense, right? Now here, when you enter this in, be mindful. What do I put here in this box? Zach? And then here? 2. Yeah, good. All right, circle problem. This is a good one. We have circle A and circle B. Logan performs 2 transformations on circle A to show that circle A is similar to circle B. One of the transformations is centered at -1, -1. Now this is kind of important where not kind of, it is. Meaning first we would need to dilate the circle and then translate it to map this onto this. All right? It's easier to do the translation first. Remember, all circles are similar. To show that, you can graph them, move one left, right, up, down, and then dilate. Okay? So I'm actually going to start off with the translation. So you do that by examining the center. How do we get from here to here? Well, we go to the right, 1, 2. So what am I going to write? Not 2. X. Yeah? Are we good there?
Yes.
Okay. Then we go 1 down, so now I'm going to write y. There you go, y minus 1. Awesome. Now, after we've done that, we are going to talk about the dilation. Okay, our radius for circle A is 1. Our radius for circle B is what? 3. Remember, a lot of people will say, oh, we added 2. No, no, no. When we talk about dilations, you're multiplying. So a way to do this is, I know you can look. You already know the scale factor is what? 3, right? You say 1 times 1 gives you 3. I mean, obviously it's 3, but we good? Not. So here I'm going to write 3x, and here I'm going to write, I'm asking. 3y, yeah. It has to be the same. Are we good? Okay. It's a guessing game. Alright, this one here, guys, I apologize, but there was no way for us to give you guys these drop-down options, so I'm just going to kind of give it to you. Talking about transforming this baby, we have this, we reflect it across one line, then we reflect it across another line, and then it says it ends up as the same translation of 4 units to the right and 4 units up. So that's where we're going to end up, all right? So I'm going to do that first. So if I look here and I go 4 right, 1, 2, 3, 4, boom, and then I go 4 up, 1, 2, 3, 4, boom, that's our prime. So T prime is 1 up and to the left, and S prime is just 1 up. All right, so a little rough, but that's all right. That's where we're going to end up, and I'm going to go ahead and give it to you. This equation here, well, let me back up. When you click on this, equations are going to drop down, right? That's what I'm talking about. So this one here is y is equal to negative x plus 6. And this one here is y is equal to negative x plus 10. All right, I'm going to now draw these mirror lines. So here, our y-intercept is at 6. You begin with B, move with M. What is our slope?
-1.
Good. It's going to be a -1 over 1. Yeah? So you go down 1 to the right 1, down 1 to the right 1. Boom, boom, boom. Y'all get that, I'm sure. All right, fling, there she is. Now let's just check this guy out and see what happens if we reflect it over. Well, this is going to end up here. This is 1 away. It'll be 1 away diagonally. They're going to do this to you, we think, hopefully, to where you can just kind of see it. Yeah? Okay. Now we're going to do the next line. Intercept is going to be at 10. Slope is -1 again, so slope is the same. The slope is the same. What do you know about these two lines?
They're parallel.
Good, they're parallel. And now look what's going to happen. This is going to end up here, this will end up here, this will end up here. That's your money. All right? Now, oh, and the answer here is because the lines are parallel. So, start off drawing that. Then what you're going to do, when you click on this, look for lines that have the same slope. All right? And do those first. So, like, drop this down, and see that first. It will save time for you. All right. Okay, this one here is a little crazy. Where's my freezer? Oh, there it is. Guess what? Select all that apply. That means you need to go through. I know you don't have scissors, but what I want you guys to do with these, take a piece of paper, rip it out, fold it, make yourself something, okay? It wants us to select all the transformations that carry this onto itself. So, if you look here, we just got to test it out. First things first, a reflection across line EK. That means if I have this line that's going this way and I reflect, this baby is going to end up that good? That's a little better, right? It's a little off. Yeah? Yeah, that looks good. Next it says a 180 degree counterclockwise or clockwise, doesn't matter, about point K. So that means this is going to end up here. And a reflection across the vertical line through point K. Guess what, guys? From here, a reflection, boom. Did we map onto itself?
Oh, yes.
Yeah, listen, you're going to have to do... It's a little messy, trust me. Oh my gosh, man. Look at how good that was.
Jeez, that was really
That
good.
was like,
Oh my god.
good job, Kat. Hair flip. Yes, honey. Yes. So, when you go, I'm not going to go through all of these for you. You do that on your own time. Something I do want to point out to you, though. Oh, my freezer. Your answers to this are here, this one, and this one. Guess what? They're the same thing, just in different orders. By the way, the answers to this I emailed via Skyward for you. Something I want to talk about real quick is rotational symmetry. If they tell you to rotate this, I don't know, 144 degrees about point K, by the way, that's important. If I tell you to rotate this about point E, then that's your center, and that thing's like going around that point. If I say here, then it's spinning around this way, yeah?
Yes.
What we need to just refresh on real quick is that if I have a circle around this and I have this going on, those would all be radii of the circle, yeah?
Yes.
Okay, what is the measure of one of those angles? To figure that out, you do 360 divided by n, which is 5. So in this case, what's the measure of one of those? Come on, y'all. 72. So this is 72 degrees. If I go and rotate this 144 about this point, this would map here. Where's my guy? Here we go. Aw. This would go here, and then it would go here, yeah?
Wow.
But it would map onto itself.
Yes.
Look at it drawing over that. That's kind of fun. All right, I'll stop.
Yes.
So just, if you see degrees like that, check the angle measure is all that I'm saying. Right? Okay. All right, this one here, don't get too hung up on it. It's telling you that the image, after we transform this, the image of E goes to 2O. So this goes to 2O here. So there's E prime. And then it says R is at 6, negative 7. So here, R prime. Before you get too hung up on anything, just read your options. Look at that one. It's the easiest one. Did we not go to the right 1, 2, 3, 4, 5, 6, 7, and then down 1, 2, 3, 4? Yeah, look at this R to this. We go to the right 7, down 4. That's your money. Okay, so once you look for the easy stuff first. Oh, all right, I like this one. All right, we have this quadrilateral dilated with a scale factor of 2.5, centered at 1, 1. Okay, so A is the center. Scale factor is 2.5, so you know it's going to get larger. Real quick, this right here, so 1, 2, that's a scale factor of 1. Our scale factor is 2.5, so I will go 1 more, and then half. That's where M prime ends up. Yeah?
Yeah.
Okay. From here to here. You know what? I'm not going to keep doing this because we don't really need to. If you look at your options, right? It's not asking us for certain coordinates. Let's just think about what's going to happen here. If this is our center, right? This dude here is going to continue to go in this direction and end up here somewhere, right? This dude here is going to go out this way and end up Here somewhere. Probably a little lower actually, but whatever. So rough sketch. It's always a rough sketch. Yeah?
Yeah.
That's what's gonna happen? So let's just go through our options because it says select all. Is it true that MA is congruent to M prime A prime?
No.
No. This is not the same size as that. Done. Will A prime T prime overlap this? Yes. Remember we talked about this because this point is located on this line and this is the center of dilation. That was done. Because the center of dilation and this are on the same line, then it's going to stay like that. Okay? So yeah, that works. Will MA prime overlap MA?
Yes.
Yes. Is the slope of HT equal to the slope of this? Yes. Absolutely. Guys, remember,
Oh, H.
this is our center. This creates parallel lines. Okay? If the center of dilation is not on the line, then it creates parallel lines. All right? If it is, then they're going to overlap. So, yes, this is true. That means they're parallel. This is something I want to talk about real quick. The area of this, the new guy, is equal to 2.5 times the area of the original. The answer is no. All right? The scale factor for the perimeter is the same. Okay, but that is linear. So let's just pretend like this. Actually, side note here. Let me do this. If I have two of these kick in, and this is 2, and this is 3, and this is 4, what would this here be if I tell you these are similar? 6. Good. What is our scale factor? 2. So if I'm talking scale factor, and this is linear, we know that their scale factor is 2. Yeah? Now let's think about something else. Their area, what's the area of that rectangle? It's an ugly rectangle, but 6. What's the area here?
24.
24. What's our scale factor from here to here?
2.
Is it 2?
Oh, wait, 4.
It's 4. Because here's what you guys have to think about now. If this was inches, it would be 6 inches squared, right? So guess what? You have to square that. So your scale factor is 4. Okay? If, let's just say I took this a step further and now created, these are going to be really ugly, just bear with me. If I created cubes, I'm going to keep these numbers simple and I just tell you that the height of this is 2 and the height of this one is, well, the height of this one is 2, the height of this one has to be 4 because they're proportional to one another, okay? What is the volume of that rectangular prism? I don't know why I called it a cube. So do area of the base times the height. So 6 times 2.
12.
So it would be 12 inches cubed, right? And this one here would be, all right, 24 times 4 is what?
100. Or
Do your, use your calc, I don't care.
96.
So 96 inches cubed. All right, what is the scale factor from here to here? Meaning, what times 12 gives you 96? 8. Good. It better be 8 because now think about this. When we're talking about the scale factor for things cubed, you have to cube your original scale factor. 2 times 2 times 2 is 8. Okay? Be mindful of that. Especially if they do something to you and they say, okay, it's in a ratio of 2 to 3, the perimeter of a figure. Well, what is the ratio of their areas? I don't know. That could be 1. It's going to be 4 over 9. You have to distribute that to both. All right? Yeah, just be careful with that stuff. That was a quick little refresher. Clear. All right. This one here, we have a trap inscribed a circle. Here's what you need to know, guys. Opposite angles in a quadrilateral inscribed a circle are supplementary. That means, on a side note, if I have this kick in here, right? This is what we call an inscribed angle. This is what we call the intercepted arc. Are we good?
Yes.
Yeah.
Okay, great. We good, Levi? Okay. If I tell you that the measure here is 200 degrees, what is the measure of that?
100.
100, yay. If I start here and go all the way around, that's 360, right? So that means this right here would have to be 160. Now if I examine this here, that inscribed angle is going to be half that. What's that going to be? 80. You guys, it will always work like that. Look, supplementary. The same thing would happen if I did it with those two. So here, I'm just going to tell you, they start out with ABC with that one. So the measure of angle ABC is equal to, now right away we're not going to use 90 because it's talking about subtracting. So we're going to say 180 minus what angle? It'll be that one, ADC.
Yeah.
Because you honestly, you're going to have to go through the options on your test, but I already know we start with this one. If I take 180 and I subtract that, I get the measure of that, right?
Right.
Okay. What, honey? No? Okay. All right, moving on. You guys are doing a great job. Keep it up. Oh man, I gotta do this too. See, I'm gonna have to re-record this, I think. Yeah, too much downtime. Will it be, guys, will it be annoying to you when you're watching this video and all this is happening? Or will you be able to fast forward it?
Yeah.
Yeah.
We can
Alright.
edit it.
I don't have time to do all that. That's the problem. That's what I started doing last time. I just y'all are- guys.
That's so weird, right?
Jeez. Yeah, go ahead, baby. All right. All right, it starts off, listen up. It starts off saying that this is parallel to this. Easy. Our ultimate goal is to prove that this plus this is equal to 180 degrees. All right, so your first line is always what they give you. Your last line is always what you're trying to prove. You guys know that by now. Now this is, see what's happening here? Hold on a second. Like why? I made that too big right there. All right, we'll make it work. We always do. Sure, whatever. All right. Now, if you guys recall, I did at the beginning of the year, you guys all cut out triangles that were different sizes, and you went like this, and like this, and like this, and then I said cut the corners, and you cut the corners off, and then you took them and you put them all together. Well, that was ugly. And you made that.
Yes.
Remember, to show that they all add up to 180 degrees. Great. Here's the deal here, because they started off talking about these two being parallel. We now need to go from there. What we have kicking is two parallel lines cut by a transversal, cut by a transversal. So the first thing I'm going to say here is that this angle is congruent to this angle. Why? I'll make sure I'm alternate interior angles, good. So you'll say, I'll go with this one. DAB is congruent to ABC. And then you already know it's alternate interior angles theorem. Next, I'm going to say that this is congruent to this. Why? Same reason, awesome, same reason. ACB, it's It's so fuzzy up here, it's crazy. Same thing, I'm just gonna go like this, because you know. All right, next it says that DAE is equal to 180 degrees. That this entire thing is 180. Personally, I would say definition of a straight line. But in this case, we're gonna just say supplementary angles. All right? I guess. Next, we are going to say, because it says angle addition, that means we are taking these three angles, so DAB, that's this dude, and this dude, and saying that they equal the whole thing. That is just angle addition. I'm just going to go like this because I don't want to rewrite everything. Is that cool? Next thing, for number 6, we need to say that these three things add up to 180 degrees. I am going to write that though. So angle DAB plus CAB plus EAC equals 180. And then again, you're going to write supplementary angles there. Okay? Now, the reason why I did that is because our last line shows substitution. Meaning what they did, because we already said that DAB, if you look at this line, is congruent to ABC, I took that and replaced it with ABC. That's our ultimate goal. Is to show that that dude, so that's done, plus BCA, now this is a little trickier here. So BCA is the same thing as ACB. Look at what they did here. They switched the order. But notice C is still the vertex, so we're good. Where we had EAC, they put this, substitution. And then of course CAB, which is this dude, stays the same. Okay? Okay. Do you guys have any questions on this?
Do you think there's a lot of this on the partitioning?
Yeah, I do. I do, and that's why I'm just, you just got to see what's happening and what's missing, you know? And don't get, like that was something tricky when I just pointed out to you how they switched the letters around. Oops. We did this one. There's a couple repeats in here. All right, this is an easy one. Gabriel wrote a partial narrative proof to prove that FD is congruent to BD, given that AD by, actually let's just read what he wrote. It is given that AD bisects EAC, so this bisects this angle here. Well guys, from that right away we can say, oh wait, then he says FDA. Sorry, FDA, that's that dude, is congruent to BDA, that's that dude. Sorry. It is given that AD bisects this and this is congruent to this. Cool. Since AD bisects this angle, well from there, right away, you know that this baby here is congruent to that baby there. That's the definition of angle bisector, and that's what he wrote. From there, he says AD is congruent to AD. What do we call that? Reflexive, God, that looks scary, sorry. Reflexive property. Right away now, we can say that triangle what is congruent to, when I say what, I mean we just need to name it. We need to say that this triangle is congruent to this triangle. Remember, our ultimate goal is to show that this is congruent to this. So when you do this drop down, however they name this one triangle, I'm just going to say FAD. All right, so triangle FAD, let's say that's how they named it, right? Is congruent to, this one really matters, how you name this one. If I started with F here, what do I need to start with on this triangle here? D. If I started with F on this one, I got to start with B on this one. Because those are the angles that are congruent. A, D. There you go. Like that. Why? Why are the two triangles congruent? Think of what we just did.
Because the A and D.
Is that what I write? Think about how we say that triangles are congruent. Think about it. We started out, we said that, okay, this is the bisector, so that means this is congruent to this. It was given to us that that was congruent to that, and then from there we said AD is congruent to itself. So then we said, okay, because of all of that, this triangle is congruent to this triangle. Why?
Angle, side, angle.
There you go, angle, side, angle. So right here you would put angle, side, angle. Now from there, he can say that this is congruent to this because of CPCTC. That never goes away. CPCTC, you guys already know. Once you show that two triangles are congruent, you can then show that all of their corresponding parts are congruent. All right? Yes, we've done that one. Sorry about the repeat. It's a repeat. Sorry about that. I'm sorry. All right, guys, this one here, do not let these scare you. Okay, this is saying we have this triangle, and then we are going to dilate it using this transformation. Centered at 0, 0. That's cool. That just means we're going to multiply all of the coordinates by 0.2. So is it going to get smaller or larger?
Smaller.
Smaller. Excellent. By the way, something you need to think about here. 0.2 as a fraction. Who said it? Excellent. It's 1/5. How'd you do that so fast?
Because it's just 2 of 10.
I did 20 over 100.
Okay, a lot of people, what they think, I'm going to just explain this for everybody. If you know it's 0.2, right, you can turn that into a percentage, which you just take your decimal and move it 2 places to the right. So 0.2 is equal to 20%. 20% is the same thing as 20 over 100. Yes, this is the very long way. I get it. Knock out those zeros. You have 2 over 10, which reduces to 1/5. Okay? Good job, Jean, for noticing that right away. All right, anyways, just go through your options. I'm just going to go like that. Because if you look, it's not asking us for any coordinates. If you look here, it says that RV, so that's the large, is equal to 5 times R prime V prime, which is the small. Is that true?
No.
Well, think about this. That's a 5, and then this is small. Sorry, I'm going to do that. If the small one is 1/5 the size, if I multiply the small side by 5, will it equal the large? Yeah, absolutely. That checks. See how I'm replacing these with large and small? It will help you. All right, let's look here. This is now saying that our small is equal to, let me back up here. It's saying that the small over the large.
Isn't that just yes?
What's that?
Can you just say yes because that's the point in front of us, so you want to go to multiply?
Well, which one here? If we have the small over the large, right?
Yeah,
Let's think about this for a second, though. What is larger, root 26 or 0.2 times root 26? I'm going to get rid of that. If I multiply something by a decimal, it gets smaller. So how they have this set up, which one of these, the one on the top is actually larger and the one on the bottom is smaller. Is that true? No. It's reversed. Do you guys see that?
Yeah.
Okay. I'm like 95% sure you're going to see this. Okay, so think about what's happening with each one. So this one here does not work. That's a big no. The next one says, okay, so this is our RT, this is our large, and this is our small. What's happening here? If I multiply our large by 0.04, will that give us the same as our small? Yes. Think about it. This is gonna make this smaller, which is gonna make it equal to that. See what I mean? It's different the way they have it here. All right, the next one says our large is equal to 0.2 times our small. That is not true. It's got to be the other way. That's what this is saying. Okay, so that one's out. What about the next one? This is saying 0.2 times the small is equal to the large. That again is out. You got to multiply the large by 0.2. Last but not least.
Yes.
Yeah, that's our money right there. You guys see it. It's the large over the small, and that works because the one on the bottom is smaller. So those three are your answers. I know, those are crazy looking, but don't let them scare you. Do what I just did. This one here is a little weird. Don't get nervous about this. Just know Catherine uses this triangle to show this. Okay, where DE is parallel to AC to prove that a line parallel to one side of a triangle divides the other two sides proportionally. So it wants to show that it's going to divide the other two sides proportionally. How can I show this to you? So it's going to be this over this is equal to this over this. Our answer here is D. Step A to the proof. I don't want you to get hung up. Just think about it. Our ultimate goal here is that it wants us to prove that we are dividing the sides of the triangle proportionally. Whatever it is asking you to prove, that is your last statement. If you look here, this says DA. So that is this dude here over BD, over that, is equal to EC over that. That is showing that this divides the sides of the triangle proportionally. If you look at C, I mean the other two don't have anything about proportion, so that's out. If you look at C, this says that BA, which is this whole thing, over BC, which is this whole thing, right away, now we're talking about two different sides of the triangle. That one is thrown out, because that's not what it wants us to do. We've done that. Ooh, I love this one. I need your help, so make sure you have your calc. This is true talk right here. The Leaning Tower of Pisa is 56.84 meters long. In the 90s, engineers retoured the building so that the angle, or that angle Y changed from 5.5 to 3.99. To the nearest hundredth of a meter, how much did the restoration change the height of the Leaning Tower of Pisa? So we have to figure out both of these. We are going to figure out when this dude is 5.5 degrees, we are going to figure out the height, which I'm going to call X. Are we good there? What are we going to use? Trig, absolutely. This is our reference angle, label from there. This is going to be our height, and this is going to be our adjacent. Awesome. All right, what do you know? What are we looking for?
You know your height, you want to find the adjacent.
Awesome. Which trig function? SOHCAHTOA. Which trig function deals with adjacent over hypotenuse? Cosine. Beautiful. So we're going to take the cosine of theta and set it equal to that. So it's going to be the cosine of 5.5 is equal to, where we see adjacent we put X, where we see height we're going to put 56.84. You already know, multiply. Okay, that is what goes in your calculator. You tell me. What'd y'all get? 56.84 times the cosine of 5.5. Talk to me. 40.28. Is that it? Yeah? Okay. Did you guys get that? Yes, no, maybe?
Wait, what is he getting?
Right there, baby. 40.28. No?
6.6.
All right, well, hold on. I haven't done it yet. So, so try it again, everybody. It's going to be 56.84 times 5.5 cosine enter. It's 56.5.
5.7.
Yeah. No, don't. Hi, honey. How are you? Don't round too much. It's going to be 56.578. I'm actually going to leave it like that. So, guys, make sure you know how to enter this in. Please, you got to be able to work these things. All right, so that's one. That's for the 5.5. Now we have to do it with the other measure, yeah? So this is going to be, what, 3.99? So guess what? Do the same exact thing, except for our angle measure is changing. That's the only thing that changed, right? Are we good? Are y'all with me?
Yes.
Thank you. Woo! So now put that in for the angle and tell me what you get. So 56.702. All right, what are we going to do with those two numbers? Subtract. Good job, Karina. So you go for it. And what'd you guys get? What is it? What does your calculator say? Yeah, it should be, you should get 0.124 in your calculator. This is, just be careful with the rounding, please, because I don't want you guys to get something wrong. I know they account for, you know, so much, but it says to the nearest hundredth of a mirror, so we meter, I don't know why I said mirror, so you would round it to that, 0.12. 0.12 meters, so was it that big of a deal? Where's my meter set? 0.12 for the meter? So they changed the height of the building that much?
Probably cost like a lot of money.
I'm sure. What was it? Was it just crush? I don't know. Something I need to Google. Alright. I like that problem so much. Ooh, another repeat. Just check the answers for that one, guys. For number 22, just check the answers. Alright? You guys know how to do that. Alright, this one here. In the diagram shown, this is a great problem. We've seen this a couple times. Alright, y'all with me, gentlemen? All this stuff is already here for us. It's asking us for the degree measure of AED. Wait. Oh, it's asking us for that. That's important. Don't get this one wrong. You guys have seen this problem before. Here's the deal. We know that this plus this divided by 2 gives us the guy on the inside. Remember these? This plus this divided by 2 gives us that. Okay? I can say 120 plus 2x divided by 2 is equal to 4x. Okay? Once I do that, I'm going to solve for x. So multiply by 2, clear the fraction. I'm going to do this quickly because you guys know how to solve equations. You get 120 is equal to 6x. What's x equal to? 20. By the way, if you write 20 down in your answer, you are wrong. It will get you. You got to take that and plug it in. I'm going to find this dude. This angle measure is going to be 80 degrees. If you write 80 degrees, you're wrong because that's not what it's asking us for. It's asking us for this. So it's going to be 100. Good, because that right there is a straight line. That's going to be 100 degrees. That's your money right there. All right? Okay. Wow, we're getting very far in here. All right, I love this next problem. Create an expression using r and x that can be used to find the length of AB in degrees. So guys, this is asking us for arc length. Then it says, create an expression that could be used to find the length of AB in degrees if circle Q were dilated with a scale factor of 3.7. Awesome. Great, great problem. So, it's asking us to use R for the radius, and it's asking us basically just for the formula for the length of that arc. Remember, arc length is equal to the measure of the angle divided by 360, or the measure of the arc divided by 360. It's the same thing, this and this, right? Times, in this case, the circumference of the circle, because it wants just that chunk. So times 2 pi r. Yeah? Yeah. But now here, because it is saying use x, the measure of that is x. That's it. So you're going to say x over 360 times 2 pi r. Question? What I would do in my answer key here is I would use these things. You guys know how to use all this. I would use even I would put parentheses here. I would use that. Okay? You good? I'll put that in parentheses just to be safe. Why not? Okay? Okay. Now, the next thing it is saying is now create an expression that could be used to find the length of AB in degrees. Why is this saying in degrees? That's interesting. So it's not asking us for length, it's asking us for the measure. Wait a minute. No, we're fine. I'm sorry. We're good. We're good. Ignore that. If circle Q were dilated with a scale factor of 3.7. So guys, that just means when we talk about scale factor, remember what we talked about before? We were talking about just multiplying the length of the radius. So you're going to multiply whatever this is by, I'm going to replace this with x instead of n. So you're going to multiply this by 3.7, right? So I would do the math. I mean, you would not be wrong if you wrote all of that. You would not be wrong. They would count it right. Okay? Or you could go a step further and you could multiply that. Are we good? I could even, I don't want to confuse you too much, but you could make this, what, 2 times that is 7.4. So you could have x over 360 times 7.4 pi r. That's how I would leave it. I mean, it's an expression, so it's not telling me to do it simply. All right, do you guys have, oh man, do I have time to show you this one? I don't. Wow, we got really far. We got really far. So I'm going to record the ones that we didn't get to and then upload it. Yay, great job.